Hi there, this is another lesson for Year 12 Discrete Maths, which is part of the OCR Further Maths course. This exercise 1A.2 on partitions and pigeonholes, and both of them are connected, but a bit loosely initially at least. So let's get cracking with this. Partitions. This is basically where we split a set of elements into two or more different subsets. So for instance, I might have 2, 3, and 4 in my set, and I want to split them up into different subsets. Now, the obvious one is you'd say, well, 2 is in one subset, and then all these curly brackets are a bit annoying. And my other subset would be, say, 3 and 4. So I've split it up into 2 and 3 and 4, and from now on, I'll just make it a bit easy for myself. Rather than doing this with proper notation, I'll just try to show it, and I will just, for now, be happy with that. So splitting it, well, I could split it like that. 2 in one subset, 3 and 4 in the other. Or I suppose I could have 3 in one subset and 2 and 4 in the other. Or I suppose I could have 4 and 2 and 3. Now, at first glance, you might think, well, that's it, done, sorted. But I'm maybe not. What if I had 2 in? 2 and 3 actually. I was just about to say, what if I had 2 and 3 instead? I have two numbers, but then I think it'd be a carbon copy of this. It would say 2, 3, and then 4, which would be the same as 4 and 2 and 3. So that seems on the face of it, that's it. But I don't have to split in that way. I could suppose have 3 different subsets, 2, 3, and 4. And suddenly I've got an extra one. And even more weirdly, I could have 2, 3, and 4 in one subset, and the other one completely blank. There you go. How do you write that? And so you can see straight away now, I've actually got 5 ways to partition these 3 numbers, 2, 3, and 4. What about if I want to partition them in a slightly different way? So I might have, I don't know, let's have a look. Here's another example, 2, 3, 5, and 7. So it's a very similar question. So now if I was to partition these, again, I'm going to use my dodgy notation. We'll see the proper notation that you'd have to do in an exam afterwards. So 2, 3, 5, and 7, well, I could have 2, 3, 5, and 7. There's one partition, really. And the other really next step, I suppose. I was going to say I was going to do the next boring one, but well, for the moment, I'll do it logically. I've done it like 1 at a time. I could, I suppose, have 2 at a time. So that would give me 2 and 3, and then I have 5 and 7 left. So I could have them separate. 2, 3, 5, 7. That seems reasonable. Or I could, I suppose, have 2 and 5, and that would leave me 3 and 7 separately. Or I could have 2 and 7, and that would leave me 3 and 5 separately. Now you can see I've got 3 different ways. I've exhausted all the 2's at the front. So what about instead I have a 3 and a 5, and that would leave me a 2 and a 7, I think. Or I could have a 3 and a 7, that would leave me a 2 and a 3. Oh, like this. And I think the last one is just a 5 and a 7, which would leave me a, I've made a mistake there. I just realized that's a 2 and a 5. And this one would be the 2 and the 3. That's why I knew I'd made a mistake. So, okay, I've got, now I suppose you can count up. I've got 6 of those. I've got 1 of those. And the next thing we say, well, what if I have 3 of them in one subset? So I go, I'll have a 2, a 3, and a 5. Or actually, before I do that, I've just realized there's another way of doing 2's. Another way of being 2's, rather than splitting this 5 and 7 off like that, I could do 2, 3 in one subset, and in the other subset, 5 and 7. Oh, I see. So here I've got 3 subsets, and here I've only got 2. I've got a 2 and a 3, and then a 5 and a 7. Oh, so right, it makes me think this next one, the 2 and the 5, I could put these 3 and the 7 together. Okay, that makes sense. The 2 and the 7 in one subset, and a 3 and a 5 in another subset. All nicely partitioned. And the next one would be a 3 and a 5, and then a 2 and a 7. And that would lead me to think there's more here. But then I've suddenly realized 3, 5, 2, 7. And the last one I did was 2, 7, 3, 5. So actually, that one's already done. And if I use these, I would count too many. I think I'd double up. So this one, I actually think there's only 3 of them. Now let's properly get onto the 3 in one batch. 3 in one batch, you'd have a 2, a 3, and a 5, and a 7 sitting there on its own. Yeah, that's reasonable. Or I could have a what would it be? Next one would be 2 and 5 and 7, or a 3 on its own, or it could be a 2 and a 3 and a 7 and a 5 on its own. I'm not sure. I'm doing this in very logical order. And another one could be, well, it'd have to be a 2 on its own, so it'd have to be a 3, a 5, and a 7, and a 2 on its own. And there's 4 ways of doing that, I think. And the last one, which I could do, I'm going to say all 4 of them together. So that would be a 2, a 3, a 5, and a 7, and a really boring empty set over here with nothing in it. And so now I've got this idea there's an extra one there. So what's that? 5, 7, 8, 14. I think there's 14 ways in total. Let's see what the answers say. And I suppose one thing I want to do is just count them quickly. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Have I miscounted? 5, 8, 9. That was lucky. There are 15. I just can't count. There are 15 ways of doing it in total. So I'm assuming they're the same ways. Now, look, that was really annoyingly tedious, but that's what partitioning is. So you'll need to know how to partition numbers, letters, whatever they are. Here's an exam question. A set consists of 5 distinct letters now, A, B, C, D, E. The set is partitioned into non-empty subsets. Non-empty, so we're not allowed that dodgy case where you just have them all together. And there are at least 2 subsets in each partition. Show that there are 15 different partitions into 2 subsets. Now, this is definitely a lot harder than the other one. Now we've got 5 letters, so I don't really want to have to list them all. Now, you could list them all, don't get me wrong. If I wanted to do this in the exam, I could do it. But notice on this one, it says it's 15. The next question, it says there are 25. So I don't really want to list them. I want to use a bit of logic. Now, a bit of logic would be, if I've got to split them into 2 subsets, as it says here, well, one of them could be, I suppose, one letter. So it could be, for instance, A, as then split with the B, the C, the D, and the E. Now, in doing that, I suppose I had 5 different ways to choose that A. And the others I don't care what they are. I've chosen the A. The others kind of fall into place. So I reckon with 1 at the front, it's a 5 ways to choose 1, 5C1. And 5C1 equals 5. And if I have instead 2 letters at the front, I've got an A and a B, and then I partition it and I leave a C, a D, and an E. I know I've written A, B there, but there's lots of different ways to choose those 2 letters. And again, I reckon with that, it's 5C2. I've got to choose 2 letters out of the 5. And if I do 5C2, I get 10, and therefore the overall total equals 15. 15 ways to get the 2 subsets. Show that there are 25 different partitions into 3 subsets. And again, you have to think, how can I split this? Partition this into 3 subsets. Well, I suppose now I'm talking, I need an A with a B and then a C, D, E. That's one way of doing it. I get a 1, and a pull. Alternatively, I would get an A, and then I have a BC, I suppose, and then I have a DE. And I don't think there's any other ways to do that. But I suppose the difficulty here is a bit like we had before. Now, if you cast your minds back here, this stage, I had to stop myself because there were some duplications. And that's the thing that you need to understand here. That if you're not careful, you're going to duplicate some of the partitions, and you're going to write, for instance, the 2735. I was going to write 3527. And that's what I'm quite pleased I made that mistake and then corrected myself, because it highlights the fact that you can count all these, but then you better be aware that you're going to get twice as many as you should get. So if that's the case here, I think using the same logic, when I do the 1, I don't think that's the problem. I think my problem will come perhaps with these other ones. So with the 1, so I think when I'm choosing my A, there's 5 ways to choose my A. I don't think there's a problem there. If you want to choose my B, I've already chosen 1 letter, so I suppose I'm timesing by the fact there's 4 ways to choose my second letter. But oh, I better be careful because AB could come up and BA could come up. So I better divide that by 2. And this is the key here. 5 times 4 is 20. Divided by 2 is... I reckon there are 10 ways of doing that. How many... What about this here where it's this 1, 2, 2 kind of scenario? So my second way of doing this is a 1. There's 5 ways of doing that. And then the BC, or again, I reckon that's... I've got to choose 4C2. And 4C2, I'll just quickly do it on my calculator. I think that's 6. So 4C2 on my calculator is 6. But I'm tempted to think I've got to do 6 divided by 2 for that. And then for the last one, I've only got 2 letters left. So I reckon that's... And I think that probably actually takes care of itself because there's not many options left at that stage. In the same way I didn't care about the CDE here. So that's like 30 divided by 2 is 15. I'm pleased by that because there are a total of 25. And I think that's the way I've got to do it. So the next part says calculate a total number of different partitions. And of course I've already now got 15 here and I've got 25 here. So I know I've got 40. How many other ways of doing it are there? Well, presumably I could split them as an A, a B, and a C, all in little, and then that would leave me a D and an E. Or I could, if I wanted to, just really be boring, A, B, C, D, E, all on their own. So given the fact that I've got these 2 options. Now, this one, actually, I quite like the look of saying DE. If I chose DE, I've got to choose 2 letters. That's 5C2. And the others, well, I'm just going to split them up. So there's into these different categories, these different subsets. So 5C2 is actually all I can do. So 10, that's one way of doing that, one way of doing that, and they'd all have to go into their own little subset. So that one, there's only 10 ways, and this is the easiest one of all. If I have them in their own individual subsets, there's only one way of doing it. There's A's in it on its own, B's on its own, C's on its own, and so on. So in total, I get 11 more, and that was 40. I reckon there's 51. If I can count, that is, I reckon there's 51 different ways of doing it. And I'm not actually too fussed about the last part of this question. I'm looking at partitions here. So look, in this question, this topic, we've basically been looking at partitions, and I hope now you understand how it is we do try to partition different sets. And if you get time, perhaps have a look at this last part D. The answers, by the way, for this, let's just have a look. Look here in the answers, they have actually listed them all. Oh, it's nasty, but that's the alternative because they've got a better way of doing it. They've said you can get 5 ways doing it this way, 10 ways doing it this way, a total of 15. And they've given reasons. They've written 5C2, for instance. But I suppose really what they're looking after was if you split it 1 off from the other 4, you get 5 ways of doing it. And if you split 2 of them off from the other 3, there are 10 ways of doing it. And then for part B, there was 10 and 15, which made the 25. And here they got an extra 10, an extra 1, which was 51. So good, but that's what we had. And as I said, I've not done part D. I'm going to leave that for you to do. And that is then the first part of the topic of partitions and pigeonholes. Now, there is actually a third one where we'll look at the pigeonholes because clearly we haven't done so yet. So thank you for watching, and next time it's pigeonholes.